everybody. Thank you for coming to this session. I'm Aruna, who's the General Chair of SIGCOMM, and we've got Jacqui from Alibaba Cloud, a staff engineer in their network research team.
Yes.
We've had the pleasure of Alibaba Cloud sponsoring SIGCOMM as well, so thank you very much for your sponsorship, and it's over to you.
Okay. So hello everyone. So thanks for the introduction. So I'm Jia Gao from network research team. So today I'm going to introduce the practical network practice in Alibaba Cloud. So Alibaba has a global network infrastructure. So we are supporting all of our businesses such as Taobao, Tmall, and Alibaba Cloud. So in the global backbone network, so we are connecting the large-scale machine learning infrastructure, and we also have the programmable gateway, which we call a smart network appliance. And we have a separate global DNS network. And as the network research team, we have published a series of papers in all of the areas above. So for the and as the scale, in general, for network research, the scale brings both the values and challenges. And so what we are doing, I look back through all the years we have the paper we have published. We are calling it a scale-driven research. So what does that mean? So our goal is to deliver predictable performance from 1 to infinite. And as a networking research team, we are quite honored to be able to involve in every step of network's lifecycle. For example, design, implementation, and maintenance. So here is a list of papers that we have published so far. So for the backbone network, we do care about the reliability, the operation efficiency, and traffic engineering. So we have published around 7 papers in the top conference, such as SIGCOMM and NSDI span through the past 5 years. And for programmable gateway, we care about development efficiency and the correctness. So for programmability, we have 3 papers that I'm honored to participate in, published in SIGCOMM and NSDI. And for data plane correctness, we have 2 papers for testing and verifying the correctness of the data plane, which is published in SIGCOMM. For large-scale machine learning infrastructure, we are honored to participate in the design of the infrastructure architecture and improve the reliability and design protocols to improve the performance. So we have around 6 papers in the past 5 years in the top conferences. All of them are published in SIGCOMM, and 2 of the papers are actually presented in the past 3 days. So for global DNS network, the correctness is and the DNS safety is our major concern. So we use the formal verification methods to verify the correctness of our DNS software implementations. So this is a whole list of the papers the network research team has published recently. And today, I think people are more interested in in our recent progress and thinking about the large-scale machine learning infrastructure. So, and that's going to be the focus of my talk today. So in the era of large language models, what we want to achieve is the exascale computing power. You can see that from the 2 figures on the left, the model size grows exponentially as the technology is advanced. So from the top corner, we can see that the transformer model actually grows 750 times over the last 2 years. But the Moore's law, I think GPU still follows, which GPU still follows, only grows twice over the past 2 years. So we want to build we have to build larger and larger systems to support the training and both training and inference of this large language model infrastructure. So, and as a result, whether the cloud company or a tech companies can provide this exascale computing power will be the core competitiveness of the company that builds this large language model, and which stems from the accelerator scale up and scale out. So, as I said before, the network research team's goal is to deliver predictable performance, and then under this context, I'm going to call it deliver predictable exascale computing power. And from our experiences, this exascale computing power actually comes from two parts. So if we want to achieve this linear scaling of large-scale GPU cluster, we have to achieve both stable high performance for stable high performance interconnect and communication co-optimized. So I'm going to break it down from the 5 layers that we have pretty familiar with. So from the toppest application layer, so for large language models, we want to achieve, for the training infrastructure, we want to achieve high model flops utilization, which is called MFU. But then as an infrastructure team, from the ground up, we need to build or support this goal from the ground up. So for the scale up and scale out topology, the requirement is we want to build a high throughput, low latency, and low complexity infrastructure. And atop of it, for the transport layer protocol, which is specific to scale out network, we want to utilize the full bandwidth provided by the infrastructure and able to sustain high concurrency, because in the large language model, the number of connections could be high, especially in MOE model. So atop of the transport layer protocol, we have the collective communication library, and the goal is to generate and execute fast CCL algorithms in order to sustain the high training throughput. And atop of the collective training library, there is the training and the inference framework, and the goal is to provide a memory efficient and performance parallelism in order to achieve this high MFU. So as a network infrastructure team, we are building this HPN 7.0, which is predictable data center network for the AI infra. So I assume, so we have a talk actually yesterday detailing all of the technical details about our 7.0 architecture. So I'm going to just explain this in brief. So in short, this HPN 7.0 is a end-host and network co-design system component. So on the left, we have the backend GPU interconnect, which mainly in charge for which we incorporate dual plane architecture that is able to provide 3.2 terabits bandwidth for each server, and we split and in the front end, which connects to our storage and VPC networks. So let's revisit the 3 layers that we have that I just shown previously. So for the scale up and scale out topology, we're using a multi-rail topology with 51.2 terabits per second switch and 40G NIC. And in the transport layer, we are designing HPCC, the congestion control algorithm, and we are building our own solo RDMA. And since there is abundant path in the topology, we're fully utilizing the path by introducing multi-pathing algorithms. And in the collective communication library, we build our own specific version called Echo, which is able to coordinate globally and is also aware of the topology and anomalies in the network. So from the performance-wise, it can. So here is a chart which is also shown in our paper, which is able to increase the CCL performance both in global reduce, multi-hour reduce. So the two shown above, we are able to increase the performance by 100%. And from the training's perspective, changing the architecture alone is able to increase the training throughput by 14.4%. So this is for the performance-wise. And the next question is how to deliver predictable performance. And let's revisit the 5 layers again. So in order to make it predictable, we have the goal is to provide a consistent high MFU. And from the infrastructure's perspective, we're using multipath and fast failure backup and recovery in the architecture to make this consistency possible. And in the transport layer, to make it predictable, the protocol is able to detect failure really fast and need to reroute when the transport path is experiencing anomalies. And in the collective communication library, it needs to be fault resilient. And when the failure happens, it needs to rebalance the communication to sustain this high bandwidth. And at the top layer, training and inference framework, so when the infrastructure fails, you actually need to redistribute the computation workload so that the overall training throughput is not affected that much. And let's go back to what we have done so far. We have a metric which is called cluster availability. And the cluster availability is from the infrastructure's perspective, how well we have done so far. So in the equation or in the formula, we can see that there are 5 parameters. So 2 are related to checkpoint, which is checkpoint interval, and the checkpoint duration, which actually means how long you are taking the checkpoint. And so on the right, we have GPU failure rate, scale of parallel training, and time to recovery. And the overall cluster availability is actually highly related to these 5 elements. And from the production measurement, we are able to achieve 98.22% cluster availability. And for the rest of the time, 0.91% we will spend 0.9% of the time localizing the failures and doing the recovery. And since the network is not perfect, so we will spend the rest less than 1% in the performance jitter. And here are some overall scores. So we are able to achieve 96% linear scaling efficiency. And after optimization, we are able to deliver we only spend 1 second in to doing the checkpoint. And we are able to continuous operation for more than 3 weeks, and we are able to recover failures in just minutes. So everything seems good, right? But I think this is just getting started. So then the problem is, what's next? So I just here to list in the same 5 layers, what are the new challenges that we are facing, and what academia can help us to improve. So one topic is always cross-layer optimization. So when we are building everything from an fragile system to a more failure resilient system, the next step is to optimize the performance, optimize the resiliency. And the key is to one of the keys is to perform cross-layer optimizations. So I will give you several examples for it. So first, when we when we look at the transport layer protocols, if we want to do cross-layer optimizations, we're going to look 1 layer above and 1 layer below. So what is the character of collective communication libraries? So currently, you have a low flow count compared with traditional data center clusters. And since it's a collective communication library, it actually has a predefined or it's actually planned communication pattern. And what's the infrastructure look like? Compared with previous like traditional data center networks, it actually has way more symmetric and fixed path. So actually in our HPN 7.0, actually any 2 hosts that across a segment is able to have more than 100 such paths. So how to take advantage of such information to deliver I will call it optimal congestion control and traffic engineering to support all the upper layers to sustain the high MFU. I think that's a really interesting and challenging topic. And give another example. So if we consider the collective communication library, so the current training and inference framework actually includes a lot of 3D parallelisms and 0-1 optimizers to reduce the memory usage, and it actually creates its own traffic pattern. So for example, I will give you several examples for it. For example, we all know that tensor parallelism actually usually is going through the scale-up network, which has really latency sensitive. So how about, but in reality, this training framework or this kind of scale-up communication is still done through the CCL library, but which means there's a long software call and has a high overhead. But what we want to do is whether we can propose a latency optimized collective library only for tensor parallelism. For example, we can call it CCL-less parallelism, which is maybe baked into PyTorch or CUDA code, which does not need to have this function calls, context switchings to deliver the ultimate performance. And I have another example. So right now there's a lot of works that is trying to optimize pipeline parallelism, data parallelism, so that the communication between the nodes in the parallelism group is overlap to the communication. So overlap to the computation. So actually that means, I was asked about this question before, so that means there is no exposed data transmission time. And that actually means if collective communication is slower by 10%, there's no impact, because all of the computation is still dominant the entire training procedure. So, but actually it's not, because 100% overlapping actually means computation and communication is, there is always an overlap of the communication and computation. And if we look at current NICO implementation closely, we know that there is a contention, or there is a sharing of the CUDA cores between the computation and the communication, which means current NICO implementation will slow down computation or take up computation's resources. And following that train of thought, actually a low computation interference communication library is a really interesting topic. And if we can achieve it, actually that boosts up both communication and computation. So there are 3 examples I have shown so far, and we can actually think more along this line. What about when we know all the infrastructure look like, can we build a collective communication library and a training and inference framework that is aware of this infrastructure pattern and same goal, right? Achieving high MFU. I think recently there are some papers talking about it. So the second future direction, in my opinion, is hardware-software co-design. Because right now the GPU cluster is so expensive and the performance is so critical that it's worthy to do dedicated hardware to implement software. So I will give you examples as well. For example, if we want to design a good transport layer protocol, we probably need to think about how to design the architecture. And that's actually one experience when we designed the HBN 7.0 architecture. So we want to simplify the topology so that we can avoid complicated transfer engineering, because any component can fail. If the infrastructure is simpler, then all the software architectures are simpler. So that's why we are introducing dual plane and a 2-tier network to avoid complex hash functions and hash collisions. Another example, maybe in the training and inference framework, if we want to, there is a lot of work actually in network computation, KV cache offloading, etc., etc. So when any component in this system has a dominant and a really high resource utilization and occupation, we can try to offload it to the hardware. And right now there's a long series of hardwares that we are able to play with, right? Switch, NICs, GPUs, FPGAs, and even memory, right? We can disks. We can do anything we want to design the system ourselves. And right now the cost is so high that any of this design makes more sense compared with all the previous generation of works. So I think we're doing quite good right now after 2 years of really busy construction and the ecosystem involvement. But everything is just getting started. And in the long run, Alibaba Network Research Team and Alibaba Networking Team is open to share our experiences and with the academia. And we are really welcome that academia can help us build a better infrastructure, more stable infrastructure, and contribute to the entire academia world and the industry ecosystem. So, sorry. Can we go back? Yeah. Sorry. So this is the end of my talk, and I'm happy to take any of questions. And that's my email here. So just shoot me an email, and we can discuss anything I've talked so far and anything you're interested in. And here I'm happy to take any questions.
Hi, thank you for a great talk. It's Junyi from Huawei. So I have a question. In your talk, you talk about programmability.
Yes.
So I'm wondering, so in this network, to what degree you think the programmability should go? Like, should we do it just in the management plane, or we should go to the control plane, or we should even go deeper to data plane?
I think so. What you're talking about hardware programmability, or just the entire?
Yeah, that's part of my question actually.
Yes, I think different levels actually require different format of programmability. For example, data plane performance is really critical, right? We're talking about end-to-end microsecond latency and even within the network nanosecond latency. So any of the software approach does not work. Right? If you think about implementing RDMA using DBTK, then no one is going to use it, right? So in that sense, actually the hardware programmability matters a lot.
Yeah.
And but I think from the management control plane and managed plane, everything right now is implemented using CPU, right? So using software, for example, people are writing Python codes to implement the training framework, like Megatron, DeepSpeed, all of them are written in Python. So I think it's already programmable. So any of the hints that you are mentioning so far, because they are already programmable enough from my perspective, is Turing complete, right? So what more are you expecting?
Yeah, but the problem is that with hardware programmability, then to be honest, the hardware we already have now, the commercial products, they are actually quite limited, right?
Yes.
And also, it makes actually the programmability makes the system vulnerable.
Yes.
Because they are too complex.
Yes.
So
this is like the beauty of research and the industry, I think.
Yeah.
So you can think about it, GPU is kind of a specialized hardware itself, right? It's programmable. It is also fixed, right? So how many tensor cores is in there, you have to bear with it. You cannot like programmably increase the number of tensor cores. But thanks to NVIDIA, right? So for decades to implement the reliability, and it's still not 100% reliable, I would say. Still has bugs, still GPU still fails, but it's very usable. But then it's more like maybe as a research team, we really want to see any of the hardware techniques to be deployed in the industry. But first, maybe we want the academia to prove us that this direction is promising. After prove that, then it's more like our industry's efforts to make it more reliable. I believe for Huawei as well, right?
Yeah.
So a lot of engineers are devoted to make the hardware more reliable. The same thing for Alibaba. We're building our own switches, right? So we're doing this Alinos or Sonic ecosystem. We're making it really, really more usable and more transparent, right? We have a lot of monitoring tools, and we are deploying this standardized ecosystem. So I think it's more like the academia needs to prove us anything is worth investigating, and it's more like industry to validate and to support products to make it more bring it into reality, bring it into our own data center, and maybe provide services to everyone.
Okay, thank you very much.
Yeah. So yeah, we don't really have to like ask questions right now because email's there. So and it's also in my personal webpage. So just shoot me an email whenever you need. And if you see any questions, like Alibaba's attitude is like open and collaborate. Yeah.
Thank you. And being the last speaker is also very hard to get people because they're.
Yes, I totally expected. I joined.
But thank you again for
thank you.
this